Okay, so now we're on to discussing sections 17.2 and 17.3. This, if you will look in the chapter, you can see this particular video. Um, go ahead and run it when you have the time. So let's take a look at this particular example. Suppose you touch one end of the wire, this wire here, to a charged plastic rod, and touch the other end to a metal ball that is initially uncharged. It's suspended here with non-conducting nylon threads. Um, so when you remove the copper wire and bring another charged object near the ball, then the ball is attracted or repelled, showing that it's become electrically charged. Electric charge has been transferred through the copper wire between the ball and the surface of the plastic rod. So in other words, you can see here that you've made a conduction, you've made a pathway for the charge, the electric charge, to make its way over to the metal ball. Now, um, if you take a charged rod that is in no way connected to that, what you're going to find is that the ball is going to move away. Why? Because you've got an electric charge here, electric charge here. The negatively charged plastic rod repels the ball. If you were to take a positively charged rod and hold it close to that metal ball, you would find that it would be attracted. They're unlike, so they pull towards each other. So the wire in that particular case is called a conductor of electricity. So if you repeat the experiment, but you use a rubber band or nylon thread in place of the wire, you're going to find that no charge is transferred. That's because those materials are considered to be insulators. Conductors permit charge to move through them, and insulators don't. So carpet fibers on a dry day are good insulators and allow charge to build up on us as we walk across the carpet. Coating the fibers with an anti-static layer that does not easily transfer electrons to or from our shoes is one solution to prevent that. And others to wind up some of the fibers around conducting cores, which I've never actually seen, but I see why it would work. So most of the materials we call metals are going to be good conductors, and most nonmetals are insulators. Within a solid metal, such as copper, one or more outer electrons in each atom become detached and can move freely throughout the material, just as the molecules of a gas can move through the spaces between the grains in a bucket of sand. The other electrons remain bound to the positively charged nuclei, which themselves are bound in fixed positions within the material. So in an insulator, there are no, or at the most very few, free electrons, and electric charge cannot move freely through the material. So some materials are semiconductors, and they kind of split the difference between conductors and insulators. They're not like copper, which is always a good conductor no matter what you do, or rubber, which is always a bad conductor no matter what you do. A semiconductor, such as silicon, can be engineered to have controllable conductivity, and that's the basis for silicon-based transistors, and that's the fundamental building block of your modern computer. Uh, Finally, you're going to note that in a liquid or a gas, a charge can move in the form of positive or negative ions. Ionic solutions are usually good conductors. So, for example, when you take table salt and you dissolve it in water, each sodium atom loses an electron to become a positively charged sodium ion, and each chlorine atom gains an electron to become a negatively charged chlorine ion. These charged particles can move freely in the solution and thus conduct charge from one region of the fluid to another. And that provides a mechanism for conductivity. Ionic solutions are the dominant conductivity mechanism in many biological processes. So this ought to be interesting to you. Salt water is salty because it contains an abundance of dissolved ions. These ions are charged and can move freely. So salt water is an excellent conductor of electricity. That's why you get out of the lake whenever you see thunderstorms around. Ordinary tap water contains enough ions to conduct electricity reasonably well, which is, why you don't use any electrical devices in a bathtub. Very bad idea. However, absolutely pure distilled water in an insulator is an insulator because it consists only of neutral water molecules. Now, induction. So let's take a metal ball like this and put it on an insulating stand so that it's just out there in space and isolated from most of the rest of the environment there. When we charge a metal ball by touching it with an electrically charged plastic rod, some of the excess electrons on the rod are moved from it to the ball, and that's going to leave the rod with a smaller amount of negative charge. In another technique called charging by induction, the plastic rod can give another object a charge of opposite sign without losing any of its own charge. So let's take a look at figure 17.5. This shows the example of a charge by induction. So a metal sphere is supported on an insulating stand. When you bring a negatively charged rod near the sphere without actually touching it, which is what you're seeing in step 2, the free electrons on the surface of the sphere are repelled by the excess electrons on the rod. So they're going to try to get as far away from that as possible, which is why they're gathering over on the right. They can't escape the sphere because there's no conduit for them to do that because of the supporting stand and the surrounding air are considered to be insulators. As a result, negative charge accumulates on the right side of the surface of the sphere, and positive charge accumulates on the left side. These excess charges are called induced charges. Now, it's the same amount of charge as what they had before. Now what you're getting is a polarization. So not all of the free electrons move to the right side of the surface of the sphere. A lot of them, but not all of them. As soon as any induced charge develops, it exerts a force or exerts forces towards the left on the other free electrons. In other words, you've got electrons gathering over there, but they're repelling like charges. So these electrons get repelled from the negative induced charge on the right and are attracted towards the positively induced charges on the left. You know, not only do you have the negative charges building up over on the right side, you got the positive on the left. So some of the electrons are going to be attracted to that. The system reaches an equilibrium state in which the force towards the right on the electron due to the charged rod is just balanced by the force towards the left due to the induced charge. If we remove the charged rod, the free electrons shift back to the left and the original neutral condition is restored. So what happens if when the plastic rod is nearby, you touch one end of a conducting wire to the right surface of the sphere and the other to the earth? In other words, you do this, you put a wire and then it goes down. So what's going to happen in that particular case? The earth is a conductor, and it is so large that it can act as a practically infinite source of extra electrons or sink of unwanted electrons. So some of the negative charge flows through the wire to the earth. Now suppose you disconnect that wire and then remove the rod. So what's going to happen? You have a net positive charge left on the sphere. The charge on the negatively charged rod has not changed during this process. It still is negatively charged as what you had before. But that negative charge that was here has now left to the ground. That leaves positive charge here on that isolated sphere. And the Earth requires a negative charge that is equal in magnitude to the induced positive charge remaining on the sphere. So charging by induction would work just as well if the mobile charges in the sphere were positive charges instead of negative charges. In other words, we're not talking about the negative charges moving around, we're talking about positive charges. Or even if both positive and negative mobile charges were present. What we're going to talk about mostly in this book is about metallic conductors in which the mobile charges are negative charges. But even in a metal, we can describe conduction as though the moving charges were actually positive. in terms of transfer of charge in a conductor, a movement of electrons to the left is exactly equivalent to a movement of imaginary positive particles to the right. In fact, when we're going to study electric currents, we're going to find that for historical reasons, currents in wires are described as though the moving charges were positive. In many cases, we may not, when a lot of these concepts were developed, we had certain ideas, and in some cases, we tried to hold to those. When excess charge is placed on a solid conductor and is at rest, the excess charge rests entirely on the surface of the conductor. If there were excess charges in the interior of the conductor, there would be electric forces among the excess charges that would cause them to move, and the situation would not be considered electrostatic. In other words, static being not moving. Polarization. A charged object can exert forces even on objects that are not charged themselves. So if you rub a balloon on a rug and then hold the balloon against the ceiling, it's going to stick, even though the ceiling has no net electric charge. After you electrify a comb by running it through your hair, you can pick up uncharged bits of paper. This is because the interaction between the balloon and the ceiling, or the comb and the paper, is an induced charge effect. So in step 2 of figure 17.5, the plastic rod was exerting a negative attractive force on the sphere, even though the charge is 0. Remember that? It's negatively charged rod. It's causing those electrons to move over there, leaving positive charges over here. That's an induced charge. So if we look at figure 17.7, this is going to show the effect more clearly. We've got a large ball that has a positive charge, and the conducting metal ball is uncharged. So when you bring this close to this, or B close to A, the positive charge on A pulls on the electrons here. In other words, the electrons here are going to be attracted to those positive charges. And that's going to set up induced charges. So you got positive charges being induced over here and negative over here. So because the negative induced charge on the surface of B is closer to A than the positive induced charge is, A is going to exert a net attraction on B. We'll get to this in section 7.4 a little bit more detail. So even in an insulator, the electric charges can shift back and forth a little when there's charge nearby. You'll see here in figure 17.8 that a static charge enables a charged plastic comb to pick up uncharged bits of paper. So you've got the comb's negative charge repels the electrons in each molecule in the paper, creating induced charges. The side of the paper facing the comb is a slight net positive charge. In other words, negatives are trying to get away from this, the positives are being attracted to that. And that's if you have a negatively charged comb. If you have a positively, then the effect is going to be reversed. Here you have a ball with a positive charge. You have a metal ball with induced charges. So you can see how this pull, this attraction to the positive charges is going to manifest itself. The comb case causes each molecule in the paper to develop induced charges, and that's an effect called polarization. The net result is that the scrap of paper shows a slight induced charge, enough to enable the comb to pick it up. So there you go. I also invite you to go over this, but for now, we need to go to 17.3. It's a short section, so I wanted to go ahead and include it in with this. An electrically neutral object is an object that has an equal number of electrons and protons. The object can be given a charge by adding or removing either positive or negative charges. Implicit in this discussion are two very important principles. First is that we have the principle of conservation of charge. The algebraic sum of all of the electric charges in any closed system is constant. Charge can be neither created nor destroyed. It can only move from one place to the next. We believe this to be universal. There's never been any experimental evidence for a violation of that principle. Even in high energy interactions in which subatomic particles are created and destroyed, the net charge of those particles is exactly constant. Boy, that's kind of weird that we haven't been able to figure out how to create or destroy that. That really is an interesting development or interesting characteristic of the universe. Second, the magnitude of the charge of the electron or proton is a natural unit of charge. Every amount of observable electric charge is always an integer multiple of this basic unit. So we say it's quantized. In other words, if it were continuous, you could assume any value you want to. But when we say it's quantized, it's a specific value or a multiple of that. So a familiar example might be if you go to pay cash for an item in a store, you have to do it in 1 cent increments. If grapefruits are selling 3 for $1, you can't buy one for 33 1/3 cents because who's got 1/3 cent? You can't divide it any more cleanly than that. And it's the same way with electricity. So the forces that hold atoms and molecules together are fundamentally electric in nature. The attraction between electrons and protons hold the electrons in the atoms. Holds atoms together to form polyatomic molecules and holds the molecules together to form solids or liquids. It accounts for phenomena such as surface tension and the stickiness of glue. Within the atom, the electrons repel each other, but they are held in an atom by an attractive force of protons in the nucleus. Well, what keeps those positively charged protons together in the tiny nucleus despite their mutual repulsion? That gets into a stronger interaction called the nuclear force.